Twin light clocks paradox. Einstein said in his special relativity that a clock in relative motion will return delayed to the starting point. Many people thought that the rapid movement was affecting the clock function. But what Einstein meant is that the space-time contracts, and the clock only shows this contraction. Langevin, friend and admirer of Einstein, created the twin paradox to prevent confusion between clock and time. According to Langevin, the twins are separated at birth, and one is placed in a very fast rocket. After several years, the traveling twin returns younger. He, Langevin, replaced the synchronous clocks with the twins and the delay in the clock with the age difference. Now everyone understands that the clock is unaffected by the high speed and is the time coordinate the one that contracts. Space-time properties change with movement. Langevin is not as well known as his paradox. A light clock is a device with a light emitter at one end and a mirror at the other. A rigid bar keeps both ends separated by a fixed distance L. The emitter sends a point of light to the other end, and it is reflected by the mirror. Upon return, the issuer is also detector and emits a new point of light as a reflection of the received, but reinforced with the intensity of the first one. The emitter detector has also an electronic counter of the point of light received. The function of the device is to measure the distance traveled by the points of light, which is equal to twice the distance L round trip, multiplied by the number n showed in the counter. The distance traveled by the light is equal to 2ln. The speed of light is constant, c, and does not vary with movement. To obtain the time elapsed, simply divide the distance traveled by the speed of light. Let us take a relative static light clock. The distance L between the emitter and the mirror is half a meter. The counter will show how many times the light has traveled the distance 2L, i.e., how many meters had traveled the light. When the counter reaches the 300 million mark, the time elapsed is 1 second. We assume that the speed of light is 300 million meters per second. We set our counter to count 1 meter each time it receives back a point of light. The counter does not know about the movement or about the distance traveled by light. It only counts how many strikes he receives. A static observer will see that the light beam of a clock in relative motion goes a greater distance, 2L second. We know that L second is greater than L because the hypotenuse is greater than the cathetus or length. The point of light takes longer to return to the meter detector. The counter will show n second, where n second is less than n, thus indicating a delay equal to 1 meter times the difference divided by c. This delay is not caused by the faulty operation of the clock, but because of the distance traveled by light, due to modification of spacetime. The exact formula of the contraction can be found on the internet looking for any of the light clock pages. Let us now take a light clock identical twin with the previous one, but we place it so that the axis and therefore the light beam run in the direction of movement. Please read the following lines from this photocopy of Eisner's article translation. You can find it also in the internet, the whole article. Eisen, in his article, Electrodynamics of Moving Bodies, tells us that the length of a rigid rod contracts in the direction of motion. Therefore, we have that separation between the emitter and the mirror of the moving body is now L prime. Applying Einstein's formula, we obtain that L is greater than L prime. The speed of light does not contract. The counter of the moving clock will show N prime. Following the same reasoning as before, we obtain that N prime is greater than N. Thus, the static clock will be behind an amount proportional to N prime minus N with respect to the moving one. The delay will be equal to 1 meter times the difference divided by the speed of light. Summarize. In the moving vertical clock, light takes L seconds. And we know that this clock is slow because L second greater than L and N second less than N, where L is the distance traveled in the static clock and N the number the static counter shows. In the horizontal clock, light travels L prime, and we know that L is greater than L prime and N is less than N prime. So the horizontal clock runs faster than the static one. Then we have this relation. If we put the two clocks in the same car or in a single rocket, we will have a clock that runs faster than and the other runs slower with respect to the static clock. Which of the two clocks tell us the real time of the moving object? Now we can enunciate the twin light clocks paradox. Two twin identical light clocks are placed on a ship. Upon returning, one of the clocks is ahead and the other is behind with respect to a clock that remains static. Simply place a clock with its axis in the direction of movement and the other with its axis perpendicular to the movement. Make your own conclusion. Please go to the reference. This software was made with a EM free PowerPoint video converter. Thank you.